Thank you.
First of all, thanks a lot for Ricardo and Alessandro for organizing this very nice workshop. I want to talk in particular on immersed methods, in our case the finite cell method, and geometric models, in particular flawed geometric models. So something which is very practical. If you talk to people in industry, then they say, well, if a geometric model would be okay, then we wouldn't have a problem. So I go through the first slides very, very quickly. I think it's not necessary to tell too much about the basics of fictitious domain methods. We embed in a larger part, we add something, and this is important in our approach, the finite cell method. We add something in the fictitious domain where we typically have not a zero there, but we have material, which is, well, from a mechanical point of view, a very soft material. So the alpha, the penalty parameter, is a finite small number, and this has a lot of consequences. One of them is, and I refer to the talk of Harald today in the morning, one of them is what we are doing in a sense just by taking this alpha to, well, say something like 10 to the minus 6, we are adding a fictitious domain stiffness, and we are also doing by default more or less diagonal scaling, which is a preconditioning, and it's important for this approach. I come back to a very recent result on this part. Harald, I got back the answer from you. I come back to this. I come back to this in a few minutes. Okay, so, well, that's the basic method. In addition to this, of course, it's necessary to define boundary conditions in the right way by integrating. We do Dirichlet boundary conditions in the weak sense by either penalty method, Nietzsche method. Most often, actually, we apply penalty because this works nicely and is very simple. And the issue of integration of cut cell is something which needs to be addressed. It was already mentioned quite a few times today. So we use space trees for integration of cut cells, moment fitting, as maybe Alexander will tell a little bit about this, or so-called, we call them smart octrees. So this is an octree where the surfaces of individual cut cells are mapped to the true surface, which brings a lot of accuracy in the system, because we do not have the kinks with a faceted surface, but we can really integrate the true surface. Okay, so just one slide about the convergence observations and also properties. We have proved this together with Monique Dauge. So this very simple problem, plate with a hole, discretized by classical low-order finite elements, the algebraic rate of convergence, discretized with a p version, a boundary-fitting p version with 4 elements. You get in this case an exponential rate of convergence. And discretized with these 4 elements, which is now finite cell, with the right integration over the cut ones, you get also the exponential rate of convergence down to a level of error which corresponds actually to your integration error. And here is where this, and the modeling error with this alpha. Here is where this alpha is coming in again. So this penalty factor of the outer space, which modifies your problem. So actually we are solving a different type of problem. We are making a modeling error, and this comes in a leveling of the curve of convergence, but this can be controlled, so you can go down to an accuracy which you would like to have. Well, just look here. We go down for a certain alpha to 10 to the to 0.1% in the energy norm, an accuracy which is beyond the usual needs in engineering. Okay, this is for smooth problems. In practice, problems are typically not smooth. They have singularities. You need local refinements. And here we use, in addition to the P ansatz spaces, which are hierarchical in our case, we use hierarchical overlays of refined spaces. So the idea is very simple in principle. So if you have a base mesh here in one dimension with a, well, say higher order approximation, which is sketched by this curve, you put on a certain part where you would like to have a refinement, you put an additional mesh, a local mesh, and add these two solutions, so you get something like this. By putting the boundary condition of this overlay to 0, you get continuity of your solution approach, and you can nest this, and this nested structure is shown in the next case. So there are different variants, what we are having here. In principle, we can do it, and I show also the 2D sketch. So it is here. The 2D, you can overlay with different polynomial degrees and different refinement levels. And this is the very recent result, which I got just over lunch. During Harald's talk, I sent an email to Munich and said, well, please, for the cut cells, deactivate the higher order nodes, only for the cut cells. And this makes exactly what was expected. It improves the condition number a lot. So this is very similar to what we heard today in the morning, the local orthogonalization of higher nodes with this hierarchy of shape functions which we are having in H and in P. So switching off the modes is of course the best optimized orthogonalization which you can make. So this works. What I got back as answer to my email, CG works much better than without this trick. So just a very recent result, 1 hour old. Okay, so everything like this works now also in the case of singularities, local refinement. We have with this local overlays, we have an exponential rate of convergence for this HP type finite cell method. Well, we started and did for a long time the integrated hierarchical Legendre polynomials, which have this nice property which I just mentioned, that you can switch on and switch off every node in principle. You can do the same with EGA, yeah? And you do it in the parameter space. And well, what you get, this is nothing else as the other word for fictitious domain is then trimming. Yeah? So this is exactly everything the same in this case, and this works in for shell-like structures. So this, we have here a mapped Cartesian grid, cut out a hole, same accuracy as if you would have a boundary conforming mesh, and same convergence properties in principle, increasing the polynomial degree for either space, either the integrated Legendre or the B-spline spaces. And well, this is a picture out of this publication, which Dominic Schillinger was the first author. So the question is this still EGA? So this is three-dimensional B-spline spaces where the surface is described by NURBS and trimmed away from the structure which would be this Lego type structure in there. So this is the connection, I would say, of the fictitious domain approaches to EGA. Well, we applied this to many different types of problems. Something very similar to what we just saw from the Valencia group. So scanned bones with screws in it. We have additive manufacturing example. Something very recent. Phase field modeling for brittle cracks, and so on, contact problem. You can do essentially everything what you do with classical finite elements with the fictitious domain. Okay, but now I come to what I promised, the CAD analysis transition, or geometric models and fictitious domain methods, and in particular, as I promised, I will focus on problems in geometric modeling. So what is the usual, or what is the, well, lecture type transition? You have a CAD model, you make a finite element mesh. There are many mesh generators around, fantastic ones, which give you for what they claim, if they want to sell it, gives you for any CAD geometry a very nice mesh, and then you make an analysis. Okay, well, this is theory. In practice, there is an enormous amount of work, typically from this to this step, because the CAD models are nearly never in practice as they should be. And I will show you for different types of CAD models, typical problems, and what is the behavior of these fictitious domain methods. Let's first have a look to constructive solid geometry. So what is used typically in the parametric CAD systems which are around in mechanical engineering. The concept is very simple, and we will see that the concept has a very close connection to what we are doing in fictitious domain methods. So a structure consists of primitives. These primitives may be very simple 3D objects, cylinders, cubes, spheres. They may also be generated primitives, which you have in the library and then use further, and Boolean operations. What you are doing in your constructive solid geometry, you are building by a kind of tree of constructions, your final structure, you're building it up, you're having unions, well, in this case, we have the union of these two cylinders. In this case, we have the intersection of the cube with the sphere, and so on, and you are building up in an easy way your structure in a very natural way, and very important, this is typically parametrized, so to each of these primitives or the mappings which are in there, you add parameters and can modify diameter of a sphere or whatsoever. Well, what is now important is that we need for fictitious domain methods, what is the information what we need? More or less the only information is a point, which is typically an integration point, inside or outside your domain. This is everything. Well, translating this to the CSG model, constructive solid geometry model, we translate the Boolean operations to logical operations, which are completely equivalent in each other. So if we have the intersection of two bodies, so of this one and this one, a point needs to be in this one and in this one. So a very simple operation. And this is what we are doing essentially for every integration point where the information is entering our system. And for all the other operations you can do it likewise. You can build up more complex kind of primitives, but it comes always back to the translation from geometry to logics in this sense. So very cheap, very simple operations, and this is what you need for the computation of fictitious domain methods. Let's look at an example, and for the next one I will show then also the flaws which are obtained in there. Okay, so this part with some parameters which are given here. Here in this case you see the tree, which is still very simple. And of course you can now have different parameters. So for example, these holes for screws can have a different diameter, which means that you add to one of these principles just another number. The tree itself stays exactly the same. And the logical operations are performed in the same logics. Of course they deliver different results for the point membership test. Well, let's look at an example. So the first part of this pipe, the first pipe which we are having here we have a spline which is defining the curvature, and the sweep path of the structure is changed by just one different control point of this curve, what would it mean in finite elements? You would have to go, if you go from this to this structure, you go all the way again. You need mesh generation, recomputation, because this is a different structure. Well, in the finite cell concept, you don't change anything, just the point membership test for these structures, which are really those where you are computing. So the cells around, the point membership delivers different results, and you have, without any change what a user would have to do, or remeshing or something like that, you get the results, and you get them very precise. So all our computations and experiments show you get them in the same range of accuracy as if you would have real finite element meshes. Well, typical flaws. Wonderful CAD model looks fantastic. You never would expect that it is a flawed model. If you do, another view of this one, if you do now mesh generation of this structure, and actually we used NetGen of Schöberl as a mesh generator, which is one of the best mesh generators which is around. So nothing against that type of mesh generation. Okay, so it makes refinements here. Is also quite clear because the edge of the cylinder is very close to the other part which we are having here. Other refinements, nevertheless it works nice for this structure. Well, and now look at these two parts. So this is one of the faces. This is one mesh, and this is another one. And this is now the typical situation where people have to fight with in practice. 80,000 elements, this is what one accepts for this problem. 1.5 million, well, why? Why is the refinement here? What is the reason for it? Well, is it a software bug? Is there an adaptive refinement there? Is it a modeling error? Or is it a small feature? And these small features are something which happen very frequently in practice. Let's look, it's only two different variants of the same stuff modeled by someone with the CSG model. So one tree is this one. So starting with the cylinder and subtracting it from the cube ends up here. The other case is someone started not with one cylinder but with two half cylinders. Well, should give the same result. If one looks close, and this is really what happens close to the size of the of machine errors, you make the union of these two, then you have the same thing. But well, now if I enlarge the structure, these two half cylinders were not glued together exactly at the same point, but there is an offset. And this offset is typically, in practice, so small that you never see it. You see it in the mesh, and then you start searching what is the problem for it. Well, looking back to my mesh, this is the right finite element mesh. But I expect that this is not the intended finite element mesh, because this is something which happened in the modeling phase, and with the designer or whoever made it did not want to have. Well, let's have a look what happens in fictitious domain methods. This is now the flawed structure. The flawed structure is put in the mesh of finite cells. The result does not see this flaw. Well, of course, now one could argue if the offset is a wanted offset, and if I want to see the singularity at that point, then this is not the right result. But I would say from a practical point, from an engineering point of view, this is what we want to have. Yeah. Otherwise, one would have to say this is something which needs to be resolved. Okay, so these are other results, stresses which we are having here. So the flaw is completely filtered out in a sense. What about boundary representation? The other typical type of defining three-dimensional problems. Again, a wonderful CAD model. So this is one of these additive manufacturing ads which show this beautiful structure. Okay, we went the same way. You get from this NURBS mesh, you get a faceted mesh. Well, again, poor NetGen. We started it, it crashed. There are 337,000 triangles with open edges not connected to another one, and 2,324 triangles with wrong orientation. So, well, if you are the poor guy who needs to compute this, then you are sitting there, but either you have a telephone number or an email address of someone in Bangladesh who fixes this for you. Then you wait 3 weeks until it comes back so that you really can compute something on it, or you have to do this work yourself. And this is an enormous amount of the long chain of the analysis chain from a CAD model to the computation. You can't compute because you don't get a mesh. Well, if one looks close to this structure, then one sees, well, here is a gap. I show the detailed view. Yeah, this is the detail. Here is a gap. NURBS are not connected closely. Yeah, but well, of course now I could say, well, I don't know what this structure is from a mathematical point of view. This is a structure which is incomputable because it's not clear what is inside outside. So as a mathematician, I could lean back and say, hey, well, give me something which is reasonable. That's not adequate for a finite element computation. From a practical point of view, I would again like to have a possibility to make a point membership test, so the inside-outside, and there is a possibility to do it with a given accuracy. So what you say again, please filter out small features until a size of something. What you are doing for this, you are generating an octree type of structure of this size. First, a boundary, and you make this is watertight if your cells are larger than the accuracy which you are asking for. Well, once you have a watertight boundary, then you can fill it inside or outside or whatsoever, and you can make a computation with a fictitious domain method without any problem. No healing of the geometry in this case, only saying please ignore features which are smaller than something. Well, the different computations, I don't want to talk about this. We've heard quite a lot about from Clemens and from the Valencia group about these types of problems. I would like to show another type of image-based computation. So something which you do with your cell phone. You can create 3D models just going around an object and making photographs with your cell phone of something. Well, we did this with this guy, which is in the Glyptothek in Munich, just next to the Technical University. So Laszlo Kudela, who did this work, just made these, I think it were 36 pictures with the cell phone camera. Then you can filter out something which is in the outer space, which is not important. What you get then is a point cloud and surface vectors. So these are not hairs of these guys, these are estimated surface vectors of this structure. Well, this is flawed. There are quite a few points which are outside and not really on the surface. Nevertheless, we have the same situation again, what we had before. What do we need? We want to have a point membership test, and we want to have it with a certain accuracy or security, I should say. Well, if you test a point, you look to the closest point of this reconstructed 3D surface, what comes out of your cell phone. From this you can decide inside or outside. You may find the next point which is an outlier, but if you do this test not for one but for several of the next points, and then you vote, am I inside or outside, then you get a good vote. Even if you are on the wrong side, what does it mean? You would take an integration point outside the structure, which does not really hurt your fictitious domain result. So you can compute immediately on this structure, on this point surface, and, well, what you're getting here, this is the resolution of the post-processing, and this is, this is the guy which we are seeing here, so a little bit problems here in the knee, but computation without any, not even a surface mesh in this case, just by the point information and the combination with fictitious domains. Okay. Some open problems. This outer space stabilization outer, well, fictitious domain stiffness works very well for linear and some nonlinear problems. For complex nonlinear problems in structural mechanics, there are quite a few open problems. I think from a practical point of view, there is a big question how to couple dimensionally reduced models, so thin-walled structures, to bulky solids. So this is also for finite elements not easy, for the classical ones. And here I think there is still a lot, there are some results, but I think there is still a lot to do. Massive parallelization, I think, is an area where a lot of work can be invested. So what are then the optimal iterative solver? How to get load balancing in the case of cut cells? Well, this area of dirty geometry is something I consider very interesting because it's, on the one hand side, it has a lot of principal questions, but I think it's also a lot of practical importance. And moving, evolving domains, more mathematical insight, I think, is necessary, and a posteriori error estimation for cut cells is something which is, I think, a large area of where much more can be done. Well, last slide, I'm at the end of my talk. I think that everyone in this room should be invited in this mini symposium, which I think about 5 or 6 persons who are sitting here in the room are organizing. We split it, the work of inviting people who are working in this area. If it happens that you are not invited, then you are invited with this slide. So the official deadline is December 15th. Maybe there is 1 or 2 days extension of the deadline. So hope to see you all
I
in.
heard from a reliable source, but then confirmed that there might be an extension.
Astonishing. So, okay, thanks a lot.